This is problem number 3 off of Unit 3, Worksheet 4. A 12-ounce can of soft drink with a mass of 340 grams at 25 degrees Celsius is placed in the freezer where the temperature is negative 12 degrees Celsius. How much energy must be removed from the soft drink for it to reach this temperature? I'll give you a hint. You're going to have to calculate Q a total of 3 times and then add all 3 Q's together. So this is my sad excuse for a freezer. We have a pop that went into the freezer because it started off around room temperature, which is 25 degrees Celsius. So if I have my pop starting off at that temperature, that's going to be my initial temperature. Now, unfortunately, you left it in the freezer for too long. It's going to get a little too cold. The freezer is at negative 12 degrees Celsius. So after a lot of time that you forgot your pop in the freezer, your final temperature is going to end up to be negative 12. So if you leave it in the freezer for that long, you can probably assume that your pop is going to freeze and become a solid. Now we can also assume that pop is mostly made out of water. And so we need to know that the freezing point of water is at 0 degrees Celsius. So at 0 degrees Celsius, you're going to have a phase change of your solid turning into a liquid. Let's draw a heating curve, actually a cooling curve of what this would look like. So contrary to popular belief, when you put stuff into the freezer, it gets colder. That's why you do a cooling curve. So we're going to start out at 25 degrees Celsius. Question is, am I going to draw a flat line right away, or am I going to draw a slanted line? Well, let's think about what's going to happen once you put it into the freezer. It's not going to immediately turn into a solid when you put it into the freezer. It first has to cool down until the point, the temperature at which it will start to freeze into a solid. Oops, I just realized I wrote this backwards. Our liquid is going to be turning into a solid. All right, back to the problem. We have to cool it down to 0 degrees Celsius first before it's going to freeze. So we're going to cool it down to 0 degrees Celsius. So we're cooling down our liquid water and our liquid pop. Then once it hits 0 degrees, it's going to start to phase change and turn into a solid. So we have a liquid turning into a solid. And then from there, I haven't reached my final temperature yet. My final temperature is negative 12 degrees Celsius. So it's going to cool down even farther until it reaches negative 12 degrees Celsius. So, like I said in my hint, we have 3 different portions to our cooling curve, and that's going to give us 3 different Q's. So let's start off calculating these Q's. Looking at just cooling down the pop from 25 to 0, I have a temperature change. So in my first Q, I'm going to calculate that using the equation that has a temperature change in it, Q equals mc delta T, where my M is the mass of the pop, 340 grams. My C, well, in this case I have a liquid, so it's going to be the specific heat of liquid water, which is 4.18 joules per gram degree Celsius. And my change in temperature is going to be the difference between my final temperature for this stage, which is 0 degrees, and my starting temperature for this stage, which was 25 degrees. So my final temperature is going to be 0, because that's when it's going to start to freeze. and my starting temperature was 25 degrees. So my change in temperature is going to be negative 25 degrees Celsius. Multiplying these out, the amount of energy that's going to be released when my pop is cooled down to its freezing point is 35,530 joules of energy. Now, your calculator is going to come out with a negative value, and that's just to indicate that this is the energy that's being released. Because as we cool a liquid down, it's going to release energy. And that means we're taking energy out of our thermal energy account. Because as we remove energy from our thermal energy account, our temperature is going to go down. So that means our particles are slowing down during this portion. All right, found my first Q. Now let's find our second Q. So let's figure out how much energy is going to be released when our liquid pop turns into a solid. Now during a phase change, our temperature is going to remain the same. So we're not going to use Q equals MC delta T. We're going to use Q equals MH, where H is either the heat of fusion or the heat of vaporization. In this case, since we're going from a liquid to a solid, we're going to use the heat of fusion of water. So our mass is 340 grams. The heat of fusion of water is 334 joules for every gram. And we're going to just multiply that out, and you should get a Q of roughly this value. And I know it's rounded, so it might not be exactly what you got, but that's okay. All right, so I found the amount of energy that's being taken away as our liquid turns into a solid, and that energy is being taken away from my phase energy account. And as I take energy out of my phase energy account, that means that the attractions between the particles are going to get stronger as they go from a liquid to a solid. Okay, third and final Q. My third Q is dealing with cooling down my solid pop now. So I'm cooling my solid pop from 0 degrees to negative 12 degrees Celsius. And so I do have a temperature change for this point. So I'm going to use Q equals MC delta T to figure out how much energy that released. So let's plug in our variables. Mass is 340 grams. We didn't lose any pop. Now, our C. Our little c is specific heat of whatever we're cooling or heating up. In this case, we're cooling down solid ice. So we cannot use 4.18 joules per gram degree Celsius because that 4.18 number was for liquid water. In this case, we have solid ice. So your worksheet should say above that the heat capacity of solid water is 2.1 joules per gram degree Celsius. And our change in temperature for this portion, again, is going to be our final temperature, negative 12 degrees Celsius, minus our initial temperature, which is 0 degrees Celsius. So we take the difference between these two values. Multiply these numbers out, and you should get the amount of energy that's released as we cool our solid down. To be 8,568 joules. Now you're going to come out with a negative number, and that just means that this energy is being released. It's being removed from our thermal energy account. Because as energy is removed from our thermal energy account, the temperature is going to drop, indicating that the particles slow down. Okay, so we found the amount of energy released as we cooled down our pop, as we solidified our pop, and then as we cooled down the solid pop. Our question asked for the entire process as it started at room temperature and as it ended at negative 12 degrees Celsius. So we have to add all our 3 Qs up. So I'm going to add my first Q, my second Q, and my third Q. When I do this, I'm going to ignore these negative values because that just means the energy is released. The energy is released the entire time. We're just trying to figure out how much of the energy is released. So when I add these numbers up, and that's why you always use pencil on a test or a quiz. You'll get that amount of energy that's being released. And that energy is going to go to your freezer, the surroundings in your freezer, and then that's going to be kicked out to your kitchen. So your kitchen is actually going to feel warmer because that energy is transferring from your pot, and it's going to go through and it's going to be transferred to your room.